Now, in this lecture, we'll answer on two questions. In the first question, we'll find out the length of line segment X, and in the second question, we'll find out the value of the shaded area inside this quarter circle. So we'll start with the first question. In the drawing, we have triangle ABC. We know that angle ABC equals to 30 degrees. Angle ACB also equals to 30 degrees. Angle DAE, this angle equals to 60 degrees. Line segment BD equals to 5 units. Line segment EC equals to 4 units. And our mission is to find out the length of line segment DE that is equal to X. Okay, so we'll focus on triangle ABC. In triangle ABC, those two angles are equal to each other. They are both equal to 30 degrees. So you write it down. Here, angle ABC. This angle is equal to this angle, that is angle ACB. And both angles are equal to 30 degrees, therefore they are equal to each other. I repeat again. In triangle ABC, angle ABC equals to angle ACB, and both angles are equal to 30 degrees, therefore they are equal to each other. And from the fact that those two angles are equal to each other, we conclude, according to the rule, that in front of equal angles in a triangle, there are equal sides. So in front of this angle, we have side AC. In front of this angle, we have side AB. And according to the rule that I mentioned, side AB must be equal to side AC. AB equals to AC. And side AB equals to side AC. In the next step, we will define side BAD as alpha, and we define side EAC as beta, and we know that the sum of the angles in any triangle is equal to 180 degrees, and especially the sum of the angles in triangle ABC must be equal to 180 degrees. So which angles we have here? We have here one angle that is equal to 30 degrees, plus this angle that is also equal to 30 degrees, plus angle alpha, plus angle 60 degrees, plus this angle that is equal to beta. In total, the sum of those angles must be equal to 180 degrees. Repeat again. The sum of the angles in triangle ABC equals to 180 degrees. So here 30 degrees plus 30 degrees is 60 degrees, and 60 degrees plus 60 degrees is 120 degrees. So we have in this side of the equation 180 degrees plus alpha plus beta must be equal to 180 degrees. So here we subtract 120 degrees from this equation, and we will get that alpha plus beta equals to 180 degrees minus 180 degrees minus 120 degrees equals to 60 degrees. So we found out that alpha plus beta equals to 60 degrees. in the next step, we will do two constructions. From point A, we will draw a straight line in such a way that the angle between the straight line and side AC will be equal to alpha. So this angle equals to alpha according to our construction. The second construction that we will do is here from point C, we will draw a straight line in such a way that the angle between the straight line and side CA will be equal to 30 degrees. So this angle equals to 30 degrees according to our construction. In the next step, we will extend the straight line A, the straight line from point A and the straight line from point C by straight line until they intersect with each other. And we will define the intersection point of the two straight lines as point F. So actually we created triangle FEC, angle alpha and this angle that is equal to 30 degrees. They are equal as they are according to our construction. Okay, in the next step we will prove that triangle ABD is congruent to this triangle, triangle AFC. Triangle ABD, this triangle is congruent to this triangle, triangle AFC. So why those two triangles congruent to each other? First of all, those two angles are both equal to alpha, therefore they are equal to each other. So here angle BAD, this angle is equal to this angle that is actually angle CAF, and they are equal to alpha, therefore they are equal to each other. I'll repeat again. Angle BAD equals to angle CAF, and both angles are equal to alpha, therefore they are equal to each other. In addition, we have already found out that side AB equals to side AC. So I write it down, AB equals to AC. I'll repeat again, AB equals to AC. And finally, those two angles, they are both equal to 30 degrees, therefore they are equal to each other. So this angle, that is angle ABD, is equal to this angle that is actually angle ACF. And both angles are equal to 30 degrees, therefore they are equal to each other. I'll repeat again. Angle ABD equals to angle ACF, and both angles are equal to 30 degrees, therefore they are equal to each other. Actually, we found that triangle ABD, this triangle, congruent to triangle AFC, according to angle side angle rule. I will explain again. In triangle ABD we have those two angles, and the side that attach to those two angles, that is AB, are corresponding congruent to those two angles, and the side that attach to those two angles, that is AC, in triangle AFC. Therefore, those two triangles can go into each other according to angle side angle rule. Triangle ABD can go into triangle AFC according to angle side angle rule. And from the fact that those two triangles can go into each other, we conclude two things. The first thing that we conclude is that side BD equals to side FC. So BD equals to FC. I'll repeat again. Side BD equals to side FC according to the rule that corresponding sides in congruent triangles are equal to each other. Those two triangles can go into each other, therefore the two corresponding sides, that is to say BD and FC, must be also equal to each other. But according to what we have, according to what is given us in the question, side BD equals to 5 units. So we can write here that side BD equals to 5 units. And from this equation, 5 equals to BD equals to FC, we derive that side FC is also equals to 5 units. Here side FC equals to 5 units, and side FC equals to 5 units. And the second thing that we'll conclude from the fact that those two triangles can go into each other is that side AD can go into side AF. AD can go into AF. Repeat again, side AD equals to side AF according to the same rule that corresponding sides in congruent triangles are equal to each other. So if we define side AD as A, here side AD equals to A according to our definition, then from this equation A equals to AD equals to AF, we'll derive that side AF is also equals to A. So here side AF is also equals to A. Okay? In the next step, we will join points E and F together by a straight line. And we'll prove that the green triangle, triangle ADE, is congruent to the orange triangle, triangle AEF. We have already found out that alpha plus beta equals to 60 degrees. Therefore, this angle that is equal to alpha plus beta, angle EAF, equals to 60 degrees, according to what we have already found out. So this angle equals to 60 degrees. So why those two triangles can go into each other? So I write it down, triangle ADE and triangle AEF. First of all, we just right now found out that those two sides are equal to each other, they are equal to A. So AD equals to AF and equals to A. So side AD equals to side AF, they're both equal to A, therefore they're equal to each other. In addition, those two angles, they are both equal to 60 degrees, therefore they are equal to each other. So here angle DAE, this angle is equal to this angle that is actually angle EAF, and they are both equal to 60 degrees, therefore they are equal to each other. I'll repeat again. Angle DAE equals to angle EAF equals to, they are both equal to 60 degrees, therefore they are equal to each other. And finally, side AE is a common side that belongs to both triangles. So this side AE equals to itself. Side AE equals to side AE is a common side that belongs to both triangles. I'll repeat again. Side AE equals to side AE is a common side that belongs to both triangles. So we actually proved that the green triangle, triangle ADE, congruent to the orange triangle, triangle AEF, according to side angle side rule. I'll explain what I mean. Here, those two sides and the angle that is included between them in the green triangle congruent correspondingly to those two sides and the angle that is included between them in the orange triangle. Therefore, those two triangles congruent to each other according to side angle side rule. Green triangle ADE, the green triangle congruent to the orange triangle, triangle AEF according to side angle side rule. And from the fact that those two triangles congruent to each other, we will conclude that side DE equals to side EF. Side DE equals to side EF. Side DE equals to side EF according to the same rule that corresponding sides and congruent triangles are equal to each other. But according to what is given as the question, side DE equals to x. So you can write here that side DE equals to x, and from this equation x equals to DE equals to EF, we will derive that side EF is also equals to x. Okay, side EF is also equals to x. Here we can write down that side EF equals to x. In the next step, I will present to you the law of cosines, and we will implement the law of cosines in this triangle, triangle EFC. So what is the law of cosines? The law of cosines is true in any triangle. So in any triangle, We have here triangle ABC, that could be any triangle. This is triangle ABC. Side AB of triangle ABC equals to A units in its length. Side AC of triangle ABC equals to B units in its length. The angle between side AB and side AC is theta. And side BC equals to C units in its length. Then, according to the law of cosines, we get that the following equation is true, that C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. I repeat again. In triangle ABC, this triangle, the following equation is true, that C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. Now we will implement the law of cosines in this triangle, triangle EFC. So I copy the triangle EFC in this new page, and we will implement the law of cosines in this triangle, triangle EFC. This angle ECF equals to 30 degrees plus 30 degrees, that is 60 degrees. Side EC equals to 4 units. Side FC equals to 5 units. And side EF equals to X. X is the line segment that we are looking for. So this is triangle EFC that I copied from the original drawing. So according to the law of cosines, we'll get here that x squared equals to 4 squared plus 5 squared minus 2 times 4 times 5 times cosine 60 degrees. Okay, so this equation is the implementation of the law of cosines in this triangle, triangle EFC. So we found out that x squared equals to 4 squared is 16 plus 5 squared is 25 minus 2 times 4 is minus 8, and minus 8 times 5 is minus 40 times cosine 60 degrees. And cosine 60 degrees is 1/2. So in total, this expression equals to minus 40 times 1/2. So actually we found out that x squared equals to 16 plus 25 is 41, and minus 40 over 2 is minus 20. So in conclusion, we found out that x squared equals to 41 minus 20. That is to say, x squared equals to 41 minus 20 is 21. So x squared equals to 21. Here we will take a root out of this equation, and we will get that x equals to the positive square root of 21. Why to the positive square root of 21? Because of the fact that x is the length, and the length must be a positive number. So x equals to either the positive root of square root of 21, or in terms of numbers it is equal to 4.58 units. So here we found out that dE that is equal to x equals to either the positive square root of 21, or in terms of numbers it is equal to 4.58 units. Okay, so we finished with the first question. In the next step I will present to you the second question. In the drawing we have a quarter circle. Inside the quarter circle we have a circle and the semicircle that are tangent to each other at this point, and also the circle is tangent to this quarter circle at this point. And we know that the radius of both the circle and the semicircle is equal to 2 units, and our mission is to find out the value of the shaded area. So because of the fact that this is a quarter circle, therefore this point must be the center of the quarter circle. So we'll define this point as point O, and point O is the center of the quarter circle. In addition, this angle must be equal to 90 degrees. It is true in any quarter circle. We define this point as A, and we define this point as B. So here OB and OA are the radii of this quarter circle. Okay, we define the point of tendency of tangent AO with this circle as point M. So point M is the point of tendency. Point of tangency of tangent OA with this circle. We define the center of this circle as point P. Point P is the center of this circle. Point M is the point on the circle itself. Therefore PM is the radius of this circle that is equal to 2 units according to what is given us the question. And we have here rule number 1. According to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. So here we have the radius OM that is drawn to the point of tendency. That is to say, it is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever we have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. So if AB is perpendicular to MO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees. So we actually can implement rule number 1 in our drawing. Why? Because in our drawing, we have the radius PM that is drawn to the point of tendency. That is to say, it is drawn to point M, that is the point of tendency of tangent OA with this circle. And whenever we have a radius that is drawn to the point of tendency, then tangent OA will be perpendicular to the radius MP. So if OA is perpendicular to MP, it means that this angle equals to 90 degrees. And this angle will be equal also to 90 degrees according to rule number 1. in the next step, from the center of this circle, that is to say from point P, we will draw perpendicular on BO. Okay? So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point P and BO as L. L is the touching point of the perpendicular from point P and BO. Okay? So actually, we created here quadrilateral PLOM that has 1, 2, 3 right angles. So I write it down. Quadrilateral LPOM has 1, 2, 3 right angles, and the sum of 3 right angles is 90 times 3 is 270 degrees, plus the size of the fourth angle, that is actually angle LPM, in total, the sum of those 4 angles must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Okay? So here we will subtract 270 degrees from this equation, and we will get that the missing angle LPM will be equal to 360 degrees minus 270 degrees. It is equal to 90 degrees, so it is a right angle. So this angle, it is a right angle, it is equal to 90 degrees. So we actually found out that inside quadrilateral LPOM we have 4 right angles, and any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So we will relate to quadrilateral LPOM as a rectangle. Okay, quadrilateral LPOM is a rectangle, and we know that the opposite sides of a rectangle are equal to each other. That is to say, in rectangle LPOM, PM equals to LO. PM equals to LO. But we have already found out that PM equals to 2. Here we can write down that PM equals to 2, that is the radius of the circle. And from this equation, 2 equals to PM equals to LO, we will derive that LO is also equals to 2 units. Here LO equals to 2 units. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we will get that in rectangle LPOM, side LP must be equal to side OM. LP equals to OM. Here, LP equals to OM according to the rule that the opposite sides of a rectangle are equal to each other. And if we define side LP as X, so here LP equals to X according to our definition, then from this equation X equals to LP equals to OM, we will derive that OM is also equals to X. Okay, side OM is also equals to X. Side OM equals to X. Okay, so in the next step we'll focus at this point that is actually the point of tendency of the circle and the quarter circle. Okay, so we define the point of tendency of the circle and the quarter circle as point K. So the circle and the semicircle have an internal latch between them at point K. That is to say, they are touching each other internally at point K. And therefore, we have a rule that states that whenever you have an internal latch between two circular shapes, like here, we have the internal latch between the circle and the quarter circle, then the center that joins, then the straight line that joins their centers together must pass for point K, that is the touching point between the two circular shapes. So, and in our drawing we know that point O is the center of the quarter circle, point P is the center of the circle, and the straight line that joins their centers together is OP. And according to the rule that I mentioned, this straight line OP the straight line OP must pass through point K. And because of the fact that the straight line OP must pass through point K, it means that line segment OPK is one straight line. So we can write down that line segment OPK is one straight line. Or in other words, you can also say that points O, P, and K, they are all located on the same straight line. So if OPK is a straight line, then OK is also a straight line. And point O is the center of the quarter circle. Point K is the point of the quarter circle itself. So this is exactly the definition of a radius. That is to say, line segment OK is the radius of the quarter circle. OK is the radius of the quarter circle. So we define the radius of the quarter circle as capital R. So here, so according to our definition, the radius of the quarter circle that is equal to capital R equals to OK. So line segment OK, it is equal to capital R, that is the radius of the quarter circle. So OK equals to capital R. And here also we have point P is the center of the circle. Point K is the point of the circle itself. This is exactly the definition of a radius. That is to say, line segment PK is the radius of this circle that is equal to 2 units according to what is given as the question. So we can write here also down that PK equals to 2 units. In conclusion, we found out that OK equals to capital R, that is the radius of the quarter circle, while PK equals to 2 units, that is the radius of the circle. And what is the length of line segment OP? The length, it is very easy to see from the drawing that the length of line segment OP equals to OK minus PK. Again, OK minus PK equals to OP. So I write it down. OP equals to OK minus PK. I'll repeat again. Line segment OP equals to OK minus PK. So OP equals to OK. OK equals to capital R, it is the radius of the quarter circle, minus PK. PK equals to 2 units, it is the radius of the circle. So in conclusion, we found out that OP equals to capital R minus 2. So here we can write down that OP equals to capital R minus 2. In the next step, we will implement the Pythagoras theorem on the right triangle, triangle OPM. So I'll copy the right triangle OPM in this new page and we'll implement the Pythagoras theorem in this triangle, triangle OPM. Side PM equals to 2 units, it is the radius of the circle. OM equals to X. And we just right now found out that the hypotenuse OP equals to capital R minus 2. So this is the right triangle, triangle OPM that I copied from the original drawing. So here by PT is the abbreviation for Pythagoras theorem. The square of the hypotenuse equals to the sum of the squares of the perpendiculars. So here the hypotenuse is OP, therefore the square of the hypotenuse is OP squared. And it must be equal to the sum of the squares of the perpendiculars, that is to say it must be equal to OM squared plus PM squared. Okay, I repeat again, according to the Pythagoras theorem in equation number 1, OP squared equals to OM squared plus PM squared. So here, OP equals to capital R minus 2, therefore OP squared is equals to capital R minus 2 squared. That is equal to OM squared. OM equals to X, so OM squared equals to X squared plus PM squared. PM equals to 2, so PM squared is 2 squared, that is 4. So in conclusion, I found out that according to the Pythagoras theorem and according to equation number 1, R minus 2 squared equals to X squared plus 4. Here we will open the brackets on this side of equation number 1 and we will get that R minus 2 squared equals to R squared plus 2 squared, that is 4, minus 2 times R times 2, that is minus 4R, that is equals to X squared plus 4. So here we have 4 on both sides of equation number 1, so 4 will get cancelled. And what is left from equation number 1 after we cancelled 4? What is left is actually X squared equals to R squared minus 4R. Okay, according to equation number 1, X squared equals to R squared minus 4R. In the next step, we'll focus at this point, that is the touching point between the circle and the semicircle, or the point of tendency between the circle and the semicircle. So we'll define this point as point H. So those two circular shapes, that is to say the circle and the semicircle, have an external notch between them at point H. And whenever you have two circular shapes that have an external between them, then the straight line that joins their centers together must pass through point H, that is the point of tendency between them. So we define the center of this semicircle is point T. So T is the center of the semicircle. Here P is the center of the circle, and the straight line that joins their centers together is TP. And according to the rule that I mentioned, this straight line TP must pass through point H. So here the straight line TP must pass through point H. That is to say, line segment THP is one straight line. Okay, so I can write down that line segment THP is one straight line. Okay, line segment THP is one straight line. Or we can also say, in other words, that points T, H, and P are all located on the same straight line. Okay? So here, point T is the center of the semicircle. Point H is the point of the semicircle itself. This is exactly the definition of radius. That is to say, TH is the radius of the semicircle that is equal to 2 units according to what is given as the question. Likewise, point P is the center of the circle. Point H is the point of the circle itself. That is to say, PH is the radius of the circle that is also equals to 2 units according to what is given as the question. So what is the length of line segment TP, or the straight line TP? The length of the straight line TP will be equal to TH plus HP. TH plus HP. I repeat again, the length of this line segment TP equals to TH plus HP. So actually the length of line segment TP equals to TH, that is 2, plus HP, that is also 2. 2 plus 2 is 4. So we found out that the straight line TP equals to 4 units. Here, point T is the center of the semicircle. Point B is the point on the semicircle itself. That is to say, TB is the radius of this semicircle that is equal to 2 units according to what is given as the question. And what is the length of line segment TL? It is very easy to see from the drawing that the length of line segment TL equals to BO, that is the radius of the quarter circle, minus BT minus LO. I'll write it down. The length of line segment TL equals to BO, that is the radius of the quarter circle, minus BT minus LO. I'll repeat again. The length of line segment TL equals to the radius of the quarter circle, that is BO, minus BT minus LP. So here TL, this line segment TL, equals in its length to BO, that is the radius of the quarter circle that is equal to capital R according to our definition, minus BT that is equal to 2 units, minus LO that is also equals to 2 units. So in conclusion, we found out that TL equals to capital R minus 2 minus 2, that is to say, it is equal to capital R minus 4. So, in conclusion, we found out that TL, line segment TL equals to R, capital R minus 4. So you can write down that line segment TL equals to capital R minus 4. Now we will implement the Pythagoras theorem on the right triangle, triangle TLP. So I'll copy the right triangle, triangle TLP in a new page, and we will implement the Pythagoras theorem on this triangle, triangle TLP. Okay. TL equals to capital R minus 4. LP equals to X. And the hypotenuse TP equals to 2 plus 2, that is 4. We have already found out that TP equals to 4 units. So actually, this is the right triangle, triangle TLP. This angle equals to 90 degrees, of course. So this is the right triangle, triangle TLP that I copied from the original drawing. So we'll implement the Pythagoras theorem on this triangle, triangle TLP. So here I will write down that by PT, that is abbreviation for Pythagoras theorem. The square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, the hypotenuse is TP, therefore the square of the hypotenuse is TP squared. And it must be equal to the sum of the squares of the perpendiculars, that is to say, it must be equal to TL squared plus LP squared. So here, TP equals to 4 units, therefore TP squared equals to 4 squared, that is 16. That is equal to TL squared. TL equals to capital R minus 4, therefore TL squared equals to capital R minus 4 squared plus LP squared. LP equals to X, so LP squared equals to X squared. So in conclusion, according to the Pythagoras theorem and according to equation number 2, we found out that 16 equals to capital R minus 4 squared plus X squared. Here we'll open the brackets on this side of equation number 2. And we'll get that according to equation number 2, 16 equals to R minus 4 squared equals to R squared plus 4 squared, that is 16, minus 2 times R times 4, that is minus 8R, plus X squared. So here we have 16 on both sides of equation number 2, so 16 will get cancelled. And what is left from equation number 2 after we cancelled 16? Here, nothing is left, is 0. And in the other side of the equation, we have R squared minus 8R plus X squared. Okay? So here we will add 8R to this equation, equation number 2, and we will get that according to equation number 2, 8R plus 0 is 8R equals to R squared plus X squared. So here we subtract R squared from this equation, equation number 2, and we'll get that according to equation number 2, 8r minus r squared equals to x squared. So, according to equation number 2, x squared equals to 8r minus r squared. While according to equation number 1, we've already found out that r squared minus 4r equals to x squared. So here we have two different expressions for x squared. In the next step we will create a third equation that states that x squared according to equation number 1 must be equal to x squared according to equation number 2. So here x squared according to equation number 1 is r squared minus 4r, and it must be equal to x squared according to equation number 2, that is 8r minus r squared. So in conclusion, according to equation number 3, we found out that r squared minus 4r equals to 8r minus r squared. Here we will add r squared to this equation number 3, and we get that according to equation number 3, r squared plus r squared is 2r squared minus 4r equals to 8r. Here we will add 4r to this equation number 3, and we get that according to equation number 3, 2r squared minus 4r plus 4r is 0 equals to 8r plus 4r is 12r. So here we will divide this equation number 3 by 2, and we will get that according to equation number 3, 2r squared over 2 is r squared, and 12r over 2 is 6r. So in conclusion, we found out that according to equation number 3, r squared equals to 6r. Here we'll subtract 6r from this equation number 3, and we get that according to equation number 3, r squared minus 6r equals to 0. So here we will take r as a common factor from this equation number 3, and we get here, so r is a common factor. What is left from r squared, whatever we took from it, r is a common factor. What is left is actually r, and what is left from minus 6r after we took from it, r is a common factor. What is left is actually minus 6. That equals to 0. So in conclusion, we found out that r times r minus 6 equals to 0. So here we will have two solutions that are possible for r or capital R. The first solution is that capital R equals to 0, but because of the fact that capital R is defined as the radius of this quarter circle, it must be a positive number. R is a length, and as a length, it must be a positive number. It can never be equal to 0. So we cancel this possibility, and we're left only with the other possibility that r minus 6 equals to 0. We will add 6 to this equation, and we get that r equals to 6 units. So we found out that the radius of this quarter circle equals to 6 units in its length. Okay? Therefore, the area of this quarter circle will be equal to the area of the circle that is pi r squared over 4. And r equals to 6, of course. And what is the area? What is the value of the shaded area? The value of this shaded area equals to the area of the quarter circle minus the area of the circle minus the area of the semicircle. repeat again. The value of the shaded area equals to the area of the quarter circle minus the area of the circle minus the area of the semicircle. So the value of the shaded area equals to the value the area of the quarter circle, that is pi r squared over 4, as I already explained, r equals to 6, minus the area of the circle, that is pi r squared, and r equals to 2, so it is pi 2 squared, minus the area of the semicircle, that is equal to pi r squared over 2, r equals to 2, so it is pi 2 squared over 2. So in conclusion, I found out that the value of the shaded area equals to pi r squared over 4 minus pi 2 squared minus pi 2 squared over 2. So here we know that capital R equals to 6, it is the radius of the quarter circle. Therefore, if R equals to 6, then R squared is 6 squared, that is 36. So this expression in total will be equal to 36 pi over 4. I write it down. The area of the quarter circle equals to 36 pi over 4 minus the area of the circle, that is pi 2 squared. 2 squared is 4, and 4 times pi is 4 pi. The area of the circle is 4 pi, so it is minus 4 pi. Minus the area of the semicircle, that is pi times 2 squared over 2. 2 squared is 4, and 4 over 2 is 2. 2 times pi is 2 pi. So in total this expression equals to 2 pi, that is the area of the semicircle. So here 36 over 4 is 9, so in total this expression equals to 9 pi, that is the area of the quarter circle. Minus 4 pi, that is the area of the circle, minus 2 pi, that is the area of the semicircle. So here 9 pi minus 4 pi is 5 pi, and 5 pi minus 2 pi is 3 pi. So in conclusion, we found out that the value of the shaded area equals to its value either to 3 pi square units, or in terms of numbers it is equal to 9.42 square units. Okay. I'll repeat again. The value of the shaded area equals to either 3 pi square units, or in terms of numbers it is equal to 9.42 square units. We finished with the second question. In the next step I will summarize the lecture. We'll start with the first question, of course. So in the drawing we have triangle ABC. Angle ABC equals to 30 degrees. Angle ACB also equals to 30 degrees. And angle DAE equals to 60 degrees. The length of side BD is 5 units. The length of side segment EC equals to 4 units. And our mission is to find out the length of line segment DE, that is equal to X. Okay, first of all, we focused on triangle ABC. That is, we have in triangle ABC, we have two angles that are equal to each other, they are both equal to 30 degrees. So, in triangle ABC, angle ABC equals to angle ACB, and they are both equal to 30 degrees, therefore they are equal to each other. From the fact that we have two equal angles in triangle ABC, we conclude that according to the rule that in front of equal angles in the triangle there are equal sides, we conclude that AB equals to AC, and therefore actually triangle ABC is an isosceles triangle. And we also know, so we defined angle BAD is alpha and angle here EAC is beta. And we also know that the sum of the angles in any triangle, and especially triangle ABC, equals to 180 degrees. So which angles we have in triangle ABC? We have here 30 degrees, and this angle also equals to 30 degrees. This angle equals to alpha, this angle equals to 60 degrees, and this angle equals to beta. So the sum of those all angles must be equal to 180 degrees. So here 30 degrees plus 30 degrees is 60 degrees, and 60 degrees plus 60 degrees is 120 degrees. So in conclusion, we found out that 120 degrees plus alpha plus beta equals to 180 degrees. Here we subtracted 120 degrees from this equation and found out that alpha plus beta equals to 180 degrees minus 120 degrees, it is 60 degrees. Alpha plus beta equals to 60 degrees. Then we did a construction. We did two constructions actually. From point A, we draw a straight line in such a way that the angle between the straight line and side AC equals to alpha. The second construction that we did is from point C, we draw a straight line in such a way that the angle between the straight line and side CA will be equal to 30 degrees. So here alpha and 30 degrees, we created them according to our construction. Then we extended the two straight lines until they intersect with each other at point F. Point F is the intersection point of the two straight lines. So we created here triangle AFC. Then we proved that this triangle that we created, triangle AFC, can go into triangle ABD. So why those two triangles can go into each other? Here, triangle. We proved the triangle ABD is congruent to triangle AFC. Triangle ABD is congruent to triangle AFC. Those two triangles can go into each other. So why those two triangles can go into each other? First of all, those two angles are both equal to alpha, therefore they are equal to each other. In addition, we have already proved that side AB equals to side AC. And finally, those two angles are both equal to 30 degrees, therefore they are equal to each other. So we actually proved that those two triangles can go into each other according to side angle side rule. According to angle side angle rule. I repeat again. We proved that triangle ABD can go into triangle AFC according to angle side angle rule. I repeat again. We actually proved that those two angles and the side that is touched between those two angles, that is side AB and triangle ABD, are corresponding congruent to those two angles and the side that is attached to those two angles, that is side AC in triangle AFC. Therefore, proved that those two triangles can go into each other according to angle side angle rule. And from the fact that those two triangles can go into each other, we conclude two things. The first thing that we will conclude that side BD equals to side FC. Here, side BD equals to side FC according to the rule that corresponding sides in congruent triangles are equal to each other. Those two triangles congruent to each other, therefore the corresponding sides must be also equal to each other. But according to what has been given to us, in the question side BD equals to 5 units. So we can write here that BD equals to 5. And from this equation 5 equals to BD equals to FC, we will derive that FC also equals to 5 units. Here FC, side FC equals to 5 units. And the second thing that we will conclude from the fact that those two triangles can go into each other is that side AD equals to side AF. Again, side AD equals to side AF according to the third rule that corresponding angles in congruent triangles are equal to each other. So if we define side AD as A, here AD equals to A, according to our definition, then from this equation A equals to AD equals to AF, we will derive that AF also equals to A. Here, AF is also equals to A. In the next step, we join points E and F together by a straight line. And we proved actually that the green triangle is congruent to the orange triangle. But before that, we have already found out that alpha plus beta equals to 60 degrees. So this angle that is equal to alpha plus beta equals to 60 degrees. So why the green triangle is congruent to the orange triangle? First of all, we just right now proved that side AD equals to side AF, that is equal to A. In addition, those two angles are both equal to 60 degrees, therefore they are equal to each other. And finally, side AE is a common side that belongs to both triangles, so side AE equals to itself as a common side that belongs to both triangles. So we actually proved that the green triangle, triangle ADE, is congruent to the orange triangle, triangle AEF, according to side angle side rule. And repeat again, those two sides and the angle between them in the green triangle congruent correspondingly to those two sides and the angle between them in the orange triangle. Therefore, those two triangles congruent to each other according to side angle side rule. And from the fact that those two triangles congruent to each other according to side angle side rule, we will derive that side DE equals to side EF according to the rule that corresponding sides in congruent triangles are equal to each other. Okay? So side DE equals to side EF. But according to what is given as the equation, side DE equals to x. So we can write here that DE equals to x. And from this equation, x equals to DE equals to EF, we will derive that EF equals to x. Here EF equals to x. X is the line segment that we are looking for. So in the next step, I presented to you actually the law of cosines. And we implemented the law of cosines in this triangle, triangle EFC. What is the law of cosines? The law of cosines is true in any triangle. So if we have this triangle that could be any triangle, triangle ABC, side AB equals to A units, side AC equals to C units, and side BC equals to C units in its length, and the angle between side AB and side AC is theta, then according to the law of cosines, the following equation is true, that c squared equals to a squared plus b squared minus 2 times a times b times cosine theta. Again, c squared equals to a squared plus b squared minus 2 times a times b times cosine theta. So we implemented the law of cosines in this triangle, triangle EFC. We know that FC equals to 5 units, EF equals to x, EC equals to 4 units, and angle ECF, this angle equals to 30 degrees plus 30 degrees, that is 60 degrees. So we implemented the law of cosines in this triangle, triangle EFC. According to the law of cosines, we get that x squared equals to 4 squared plus 5 squared minus 2 times 4 times 5 times cosine 60 degrees. Again, x squared equals to 4 squared plus 5 squared minus 2 times 4 times 5 times cosine 60 degrees, according to the law of cosines. So here x squared equals to 4 squared, that is 16, plus 5 squared, that is 25, minus 2 times 4 is minus 8, and minus 8 times 5 is minus 40, and cosine 60 degrees equals to 1 half. So in total, this expression equals to minus 40 times 1 half. So in conclusion, we found out that x squared equals to 16 plus 25 minus 40 times 1 half. So x squared equals to 16 plus 25 is 41, and minus 40 times 1 half is 20. So in conclusion, we found out that x squared equals to 41 minus 20, and 41 minus 20 is 21. So x squared equals to 21. We took a root out of this equation, and we got that x equals to the positive square root of 21, or in terms of numbers, it is equal to 4.58 units. And the reason that x equals to the positive root of square root of 21, because of the fact that x is a length, it must be a positive number. Therefore, x equals to either the positive root of square root of 21, or in terms of numbers, it is equal to 4.58 units. So we finished with the first question. Then I presented to you the second question. Here in the drawing we have a quarter circle. Inside the quarter circle we have a circle and a semicircle that are tangent to each other at point H, and the circle is tangent to the quarter circle at point K. And our mission, we know that the radius of the circle is 2 and the radius of the quarter circle is also 2, and our mission is to find out the shaded area, or the value of the shaded area. Okay, so first of all, in any quarter circle, this point is the center of the quarter circle, so point O is the center of the quarter circle, and angle LOA or BOA is always equals to 90 degrees. So here we have tangent OA that is tangent to this circle is point M. Point M is the point of tendency of tangent OA with this circle. And we have rule number 1. According to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. Here we have the radius OM that is drawn to the point of tendency, that is to say it is drawn to point M, that is the point of tendency of tangent AB with this circle. And whenever we have a radius that is drawn to the point of tendency, then tangent AB will be perpendicular to the radius MO. So if AB is perpendicular to MO, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees. We actually implemented rule number 1 in our drawing. In our drawing we have the radius PM that is drawn to the point of tendency, that is to say it is drawn to point M, that is the point of tendency of tangent OA with this circle. And whenever you have a radius that is drawn to the point of tendency, then tangent OA will be perpendicular to the radius MP. So if OA is perpendicular to MP, it means that this angle equals to 90 degrees and this angle also equals to 90 degrees according to rule number 1. So we have here two angles that are equal to 90 degrees, and then from point P, that is the center of the circle, we draw perpendicular on BO. So this angle equals to 90 degrees and this angle also equals to 90 degrees according to our construction. And we define the touching point of the perpendicular from point P and BO as L. L is the touching point of the perpendicular from point P and BO. So we created quadrilateral LPOM that has 1, 2, 3 right angles. So inside quadrilateral LPOM we have 3 right angles, and the sum of 3 right angles is 90 times 3 is 270 degrees, plus the size of the fourth angle that is actually angle LPM. In total, the sum of those 4 angles must be equal to 360 degrees according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Here we subtract 270 degrees from this equation and found out that the missing angle LPM equals to 360 degrees minus 270 degrees, it is 90 degrees. So this angle, it is a right angle. So we actually found out that inside quadrilateral LPOM we have 4 right angles. And any quadrilateral that has 4 right angles must be at least a rectangle if not a square. So we relate to quadrilateral LPOM as a rectangle. And we know that the opposite sides of a rectangle are equal to each other. That is to say, rectangle LPOM, PM must be equal to LO. PM equals to LO, but we have already found out that PM equals to 2. So from this equation 2 equals to PM equals to LO, we will derive that LO also equals to 2 units. Here LO equals to 2 units. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we will get that side LP must be equal to side OM. LP equals to OM, and if we define LP as X, here LP equals to X according to our definition, then from this equation X equals to LP equals to OM, we will derive that OM also equals to X. Okay, then we focused at point K, that is the touching point of the circle and the quarter circle. At point K, we have an interval length between the circle and the quarter circle. And whenever you have an interval length between two circular shapes, then the straight line that joins their centers together must pass through point K, that is their touching point. Here, point O is the center of the quarter circle. Point P is the center of the circle. And the straight line that joins their centers together is OP. And according to the rule that I mentioned, the straight line OP must pass through point K, that is their touching point. Or in other words, we can say that line segment OPK is one straight line. So here, line segment OPK is one straight line, or we can also say that points O, P, and K are all located on the same straight line. Okay, so if OPK is a straight line, then OK also must be a straight line. So point O is the center of the quarter circle. Point K is the point of the quarter circle itself. This is exactly the definition of a radius. That is to say, OK is the radius of the quarter circle. Here, OK is the radius of the quarter circle. So we defined the radius of the quarter circle that is equal to capital R according to our definition. So here, OK equals to capital R. And here, P is the center of the circle. K is the point of the circle itself. That is to say, PK is the radius of the circle that is equal to 2 units according to what is given us the question. So in conclusion, we found out that PK equals to 2 and OK, it is the radius of the quarter circle that is equal to capital R according to our definition. So what is the length of line segment OP? The length of line segment OP equals to OK minus PK. Again, OK minus PK equals to OP. Here OP equals to OK minus PK. So OP equals to OK, that is capital R, it is the radius of the quarter circle, minus PK, that is equal to 2, it is the radius of the circle. So in conclusion, we found out that the length of line segment OP equals to capital R minus 2. Then we implemented the Pythagoras theorem on the right triangle, triangle OPM. So I copied the right triangle OPM in this new place and we implemented the Pythagoras theorem on the right triangle, triangle OPM. We just right now found out that the hypotenuse OP equals to capital R minus 2. PM equals to 2 units, it is the radius of the circle, and OM equals to X. Here, by PT is by Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is OP, so the square of the hypotenuse is OP square. And it is equal to the sum of the squares of the perpendiculars, that is to say it is equal to PM square plus OM square. Okay, so OP is capital R minus 2, therefore OP square is capital R minus 2 square. OM is X, so OM square is X square plus PM square. PM is 2, so PM square is 2 squared, that is 4. So in conclusion, according to equation number 1 and Pythagoras theorem, we found out that R minus 2 square equals to X square plus 4. Here we open the brackets on this side of equation number 1 and found out that R minus 2 square equals to R square plus 2 square, that is 4, minus 2 times R times 2, that is minus 4R. So here R square plus 4 minus 4R equals to X square plus 4. Here we have 4 on this on both sides of the equation, so 4 will get cancelled and we left only with X square, that is equals to R square minus 4R. So this is equation number 1 that states that X square equals to R square minus 4R. Then we focused at point H. Point H is the point of tendency or the touching point of the semicircle and the circle. So at point H we have an external lunge between the semicircle and the circle. And whenever you have an external lunge between two circular shapes, it means then the straight line that joins their centers together must pass through the touching point of the two circular shapes. Point P is the center of the circle. Point T is the center of the semicircle. And the straight line that joins their centers together is PT. And according to the rule that I mentioned, the straight line PT must pass through point H, that is their touching point. That is to say, PHT is one straight line, or THP is one straight line. So if THP is one straight line, then TP is also must be a straight line. TP is a straight line. So what is the length of the straight line TP? From the drawing it is very easy to see that TP equals to TH plus HP. Again, TP equals to TH plus HP. Here point T is the center of the semicircle. Point H is the point of the semicircle itself. That is to say TH is the radius of the semicircle that is equal to 2 units. Here point P is the center of the circle. Point H is the point of the circle itself. Therefore PH is the radius of the circle that is also equals to 2 units. So here TH equals to TP equals to TH plus HP. So TH equals to 2 and HP also equals to 2. So in conclusion found out that TP equals to 2 plus 2. 2 plus 2 is 4. So TP equals to 4 units. The hypotenuse TP equals to 4 units of triangle TLP, the right triangle TLP. What is the value of TL, line segment TL? First of all, what is the value of BT? Point T is the center of the semicircle. Point B is the point on the semicircle itself. This is exactly the definition of a radius. That is to say BT is the radius of the semicircle that is equal to 2 units according to what is given as the question. So, what is the value of line segment TL? It is very easy to see from the drawing that TL equals to BO, that is the radius of the quarter circle, minus BT minus LO. I'll repeat again. TL equals to BO, that is the radius of the quarter circle, minus BT minus LO. Okay? So TL equals to BO, that is the radius of the quarter circle, that is equal to capital R according to our definition, minus BT, that is 2, minus LO, that is also 2. So in conclusion, we found out that TL equals to R minus 2 minus 2. That is to say TL equals to capital R minus 2 minus 2 is minus 4. So TL equals to capital R minus 4. Okay? So here TL equals to capital R minus 4. And we have already found out that the hypotenuse TP equals to 4. So I copied the right triangle TLP in this new page and we implemented the Pythagoras theorem on this right triangle TLP. We just right now found out that TL equals to capital R minus 4, the hypotenuse TP equals to 4, and LP equals to X. And this again equals to 90 degrees according to our construction. So according to the Pythagoras theorem, pi PT is the abbreviation for Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is TP, so the square of the hypotenuse is TP squared. It must be equal to the sum of the squares of the perpendiculars, that is to say, it must be equal to TL squared plus LP squared. TP is 4, so TP squared is 4 squared, that is 16. TL is R minus 4, so TL squared is R minus 4 squared. LP is X, so LP squared is X squared. So in conclusion, we found out that 16 equals to R. We open the brackets here in the side of the equation. So here 16 equals to R minus 4 squared. R minus 4 squared equals to R squared plus 4 squared, that is 16. Minus 2 times R times 4, that is minus 8R plus X squared. We have 16 on both sides of the equation, so 16 will get cancelled. What is left from equation number 2 after we cancel 16? What is left is that in this side of the equation nothing is left, so we have 0. That is equal to R squared minus 8R plus X squared. So we added 8R to this equation, equation number 2. 0 plus 8R is 8R. That is equal to R squared. 8R minus 8R is 0. So 8R equals to R squared plus X squared. We subtracted R squared from this equation, equation number 2, and we found out that 8R minus R squared equals to X squared. This is according to equation number 2, but according to equation number 1, we have already found out that X squared equals to R squared minus 4R. So we have two different expressions for X squared. Therefore, we created equation number 3 that states that X squared according to equation number 1 must be equal to X squared according to equation number 2. So x squared according to equation number 1 is r squared minus 4r, while x squared according to equation number 2 is 8r minus r squared. And those two expressions must be equal to each other. That is to say, r squared minus 4r equals to 8r minus r squared. Here we added r squared to this equation, equation number 3, and we found out that r squared plus r squared is 2r squared. So here, in this side of the equation, we have 2r squared minus 4r, that is equal to 8r. Here we added 4r to this equation, equation number 3, and we have 4r minus 4r is 0. So in this side of the equation, we left only with 2r squared. In the other side of the equation, we have 8r plus 4r is 12r. So in conclusion, we found out that according to equation number 3, 2r squared equals to 12r. Here we divided this equation, equation number 3 by 2, and we got that 2r squared over 2 is r squared, and 12r over 2 is 6r. So in conclusion, we found out that according to equation number 3, r squared equals to 6r. Here we subtracted 6r from this equation, equation number 3, and we found out that r squared minus 6r equals to 0. So here we took r as a common factor from these expressions, and so r is a common factor. What is left from r squared after we took from it r squared as a common factor? What is left is actually r. And what is left from minus 6 after we took from it r as a common factor? What is left? It is actually minus 6. So in conclusion, we found out that according to equation number 3, r times r minus 6 equals to 0. So here we will have two solutions that are possible for r, either r squared equals to 0 or r minus 6 equals to 0. But because of the fact that r is the radius, or capital R is the radius of the quarter circle, it must be a positive number. It can never be equal to 0. So we cancel this solution, and we left only with the second solution that r minus 6 equals to 0. R minus 6 equals to 0, so here we added 6 to this equation and found out that r, the radius of the quarter circle, equals to 6 units. And therefore, the area of the quarter circle will be equal to the area of the circle, that is pi r squared over 4. And what is the value of the shaded area? The value of the shaded area equals to the area of the quarter circle minus the area of the circle minus the area of the semicircle. I repeat again, the value of the shaded area equals to the area of the quarter circle minus the area of the circle minus the area of the semicircle. As I've already mentioned, the area of the quarter circle equals to the area of the circle, that is pi r squared over 4. And r equals to 6 units. The area of the circle equals to pi r squared, and r equals to 2, so it is pi 2 squared. And the area of the semicircle equals to pi r squared over 2, of course. And 2 equals to 2, so it is pi 2 squared over 2. The area of the quarter circle is pi r squared over 4, and r equals to 6. So r squared is 6 squared. So in total, this expression equals to 36 pi over 4. That is the area of the quarter circle. Minus the area of the circle, that is pi 2 squared. 2 squared is 4, and 4 times pi is 4 pi. So the area of the circle is 4 pi. Minus the area of the semicircle, that is pi 2 squared over 2. 2 squared is 4, and 4 times pi is 4 pi. And 4 pi over 2 is 2 pi. So in conclusion, we found out that the shaded area equals to 36 pi over 4 minus 4 pi minus 2 pi. 36 over 4 is 9, so in total this expression equals to 9 pi. 9 pi is the area of the quarter circle minus the area of the circle, that is 4 pi minus 2 pi equals to the shaded area. 9 pi minus 4 pi is 5 pi, and 5 pi minus 2 pi is 3 pi. So in conclusion, we found out that the value of the shaded area equals to either 3 pi square units, or in terms of numbers, it is equal to 9.42 units. I repeat again, the value of this shaded area equals to either 3 pi square units, or in terms of numbers, it is equal to 9.42 square units. Okay? Thank you very much.